Okay, so now we're going to take a look at a few functions and we're going to figure out what their domains are. So let's start with the first one. We've got f of x is equal to x squared plus 1. So start by just thinking about what that function does in ordinary language. When you give it an input value, first thing it's going to do is it's going to square it. Okay, so does that cause any restrictions? Is there any real number that you can't take the square of? And the answer is no, right? Any number can be multiplied by itself. So therefore, any number can be squared because that's what it means to square a number. You multiply it by itself. But then you might say, okay, well, that's not the whole story. We're not just squaring the number. We're also going to add 1 afterwards. But that's also no problem, right? There's no real number that you can't add 1 to. So no matter what you get when you square the input value, you can always add 1 to the result. So again, there's no problem. There's no restrictions here. So usually what you say in this case, I mean, it says to sketch the domain of each function and write it using interval notation. Well, if the domain is everything, it kind of maybe feels a little bit weird to sketch it. Whatever, let's sketch it anyway, right? Let's sketch the whole real line, right? If you were sketching an interval, you'd pick maybe endpoints and shade in between, right? But we're not going to do that because we're shading the whole real line. So we're shading everything. This is what it means to sketch the domain if the domain happens to be the set of all real numbers. And then in interval notation, you can let's write it this way. We'll write DOM of f. That's this. We'll say that's short for domain, right? So that's the short for the domain of the function f is equal to. Let's write it as all real numbers. Now it says write it in interval notation. So if you really want to be picky, you can say the domain of f is equal to the interval, and then just don't specify a lower endpoint, write negative infinity instead, and then don't specify an upper endpoint, write positive infinity instead. So there you go. You've written the real line as an interval, and that's totally fine. But it's also completely fine to write it like this. Both representations of the domain are perfectly fine, but this technically uses interval notation. Okay, since everything is literally the answer, I'm not going to, it kind of seems silly to put a box around anything because it's all of that is directly answering the question. So let's just move on to the next one. We've got a function g defined by the rule g of x is equal to 1 over x. Okay, so again, in ordinary language, what does this function do? You give it an input value, and then it divides 1 by whatever that input value was, right? So then that's going to lead to the question, is there any real number that you cannot divide 1 by? And the answer is yes, there is. There's one number that you can't divide 1 by. In fact, you can't divide anything by it, and that is 0. Right? We cannot plug in 0 to this function because then we would be dividing 1 by the number 0, and that's not defined. Okay, so let's when we sketch it, we're going to almost sketch the whole real line, but we're not going to include the point 0. So let's just draw an open dot at 0. Then we'll sketch everything to the left of it, including the arrow at the end. Then we'll sketch everything to the right, including the arrow. And that's what it means to sketch the entire real line except that one point that we're removing, and that's 0. Okay, and to write it in interval notation, you're not going to be able to write it as a single interval because it's split up into 2 intervals, right? You've got one interval here and another interval here, but we're going to paste them together with the union symbol. So we'll write the domain of G is equal to, well, we want all the numbers that are less than 0. So that's the interval from negative infinity to 0. And then we're going to take the union of that interval with the interval consisting of all positive numbers, so the numbers that are all greater than 0. So that union sign means put them together into one set. And that's how we can write the domain in interval notation. Okay, and then lastly, we've got h of x. We've got this function h defined by h of x is equal to the square root of x. So, okay, so what's going to happen? You plug in an input value, and then h is going to go take the square root of it. So are there any numbers that you can't take the square root of? And the answer is yes. There are some numbers that you can't take the square root of, and that is negative numbers, right? You can't take the square root of a negative number. So what's the domain? It's going to just be all positive numbers, except also 0, because you can take the square root of 0, right? The square root of 0 is just 0. So it's actually not just positive numbers, but all the positive numbers and 0. So a simpler way to say that would just be the set of all non-negative numbers. So, and again, let's start with the sketch. So here's 0. We're going to shade all the positive numbers, but then also 0. So we'll have that closed dot there. And then we can say that the domain of H, in interval notation, this is going to be a closed bracket for 0, square bracket for 0, and then the infinity symbol instead of an upper bound. So that's the domain of the function H. So you just got to think it through, right? When you start to compose functions and put several functions together to make more complicated functions, then this gets more challenging. And actually, we will see a couple more examples before this section's over. But before we get on to some harder ones, let's also take a look at the range of a few functions. Okay, so remember the range is the set of all possible output values that you'll encounter with a function, right? So let's start with this function. So what is this function? This is actually has a name. This is called the identity function because it doesn't really do much. Okay, you plug it in an input value and it gives you back the same value. That's what this function does. F of x equals x. That's what that rule is telling you. You plug in a value, it just sends you back that exact same value as an output value. So, well, first of all, you might want to think about its domain. Its domain is all real numbers, right? That's defined for any input value. So, and that's what will help you figure out what the range is going to be. So what happens if you take all the real numbers and you plug them into F and you write down all those output values and you put them together into a set? Well, you can't actually do that because it's infinite, right? But you're going to get all real numbers, right? If you plug in any number and then it just gives you back the same number, the range of that function is going to be all real numbers. So let's use this notation, RAN, that's short for range. You can write the whole word range if you want. RAN of F, so that's the range of F, is just going to be the set of all real numbers. Or, again, if you want to write it in interval notation, we could say the range of F is from negative infinity to infinity. And when you're talking about range, it's more complicated, right? The range is more complicated, so let's give a justification here. What we're going to do is this. We're going to just say, okay, if y is any real number, right, take any real number at all, let's justify why is it that we know for sure that that's going to show up as an output value, because that's what we just claimed, right? We said that the range of f is all real numbers, meaning that every real number will show up as an output value for the function f. So why is that the case? Well, we'll justify it by this way. We'll start by just assuming we've got some real number y, and then we'll demonstrate how is it going to appear as an output value. Well, just plug that same value in to f, right? F of y. What is f of y? It's just, well, what does the function f do? You plug in a value and it just gives you back that same value. So f of y is just going to be y. And look, there you go. Here's y. It showed up as an output value, right? So there you go. That's justification, right? There's not much to say. How about the next one? So, oh, and I guess we're supposed to sketch it too, aren't we? So maybe I'm being a bit obsessive here to follow the instructions, but nonetheless we'll sketch the range. It's a good habit to follow instructions. Even though we already sketched it up here, but that was the domain of a different function. That was the domain of this function up here. Here's a sketch of the range of this function. Okay. Now, what about this function g? G is defined by the rule g of x is equal to x squared. So, okay, g you plug in an input value and g is going to square it and send back the result. So well, the domain is all real numbers, right? There's no restrictions on what you can plug into that function. You can plug in any real number you like. What could possibly show up as an output value? Well, if you're squaring the number, you're never going to get a negative number back as output, right? Because the negative numbers can never be written as the square of something else, which is why you can't take the square root of a negative number, right? So for that reason, it looks like we're only going to get positive numbers back. But also, we're also going to get 0, because if you square the number 0, you'll get 0. Okay, so that's why we know we'll also get 0 as an output value. But let's write this out. Just me saying it out loud is a little bit hard to process. So first of all, let's write out what the range will be, and then we can justify it in a moment. So the range of the function g is the set of all positive numbers, but also 0. Okay, so why is that? Well, there's two claims here. There's two things to really justify. First of all, why is it that we won't get negative numbers, right? Because I'm claiming in here, first I'm claiming that we won't get any negative numbers in the range, but then I'm also claiming that we will get every positive number along with 0 in the range. And if we can justify those two statements, then that will be enough, right? So the first part is, well, take any input value at all. Let's let x be any input value. Well, then g of x is x squared. And here's the logic, right? The square of something can never be negative. It always has to be greater than or equal to 0. So we can say this is greater than or equal to 0. So what this does, what we've justified here, is that there's no way you're ever going to get a negative number in the range of g. Okay, so that's half of it. Well, how do we know that we're going to get all the other numbers? Well, here's the rest of it. So let's start by saying, okay, we'll take y to be any number that's greater than or equal to 0. And my claim is that that will be in the range of g. So take any non-negative number y, and it will show up as an output value for the function g. So, well, what would the input value be? Well, if it's a positive number, it's got a square root. And if you plug its square root into g, you're going to end up getting the original value back. You're going to get y. So let's plug the square root of y into g. So g of the square root of y, that's going to be, well, the square root of y squared. And the square root of y squared, you're gonna cancel the square root with the square, and you're just going to end up with y. And there you go. That means we got y appearing as an output value. It's g of something, right? That's what it means to be an output value. You can write it as g of something. And the only thing we assumed here is that y was some non-negative number, and that was already enough for us to be able to show that it shows up as an output value. So that's the justification. And then the sketch, as usual, it's all these numbers here. But we also want to include 0. Okay, so that's your sketch. Okay, so for the third one here, this looks very similar to the second one in part B, right? So we've got a function h. It's defined by the rule h of x is equal to x squared plus 1. So you square the input value and then add 1. And that's almost the same as part B, which is defined by the rule of taking your input value and then just squaring it. The only difference is in part C, we're adding 1 afterwards. So start with the x squared. If you were just looking at x squared, we already know what the outputs of that function would be, right? That's going to give you all the non-negative numbers, all the non-negative real numbers as output values. But then we're going to add 1 to all those numbers. So we're going to shift them all up by 1. So ask yourself, if you have, I'll just look at the sketch, because this is where the sketch is helpful. If I take every number in this set that's shaded like this, and I add 1 to all of them, what's going to happen? I'm going to essentially shift every number 1 unit to the right. And then what I'm going to end up with is you're going to get the range of h is equal to the closed interval from 1 to infinity, right? And once I sketch it, you'll definitely see why. Because really all I'm doing is I'm just taking all of the numbers in this set and I'm shifting them 1 unit to the right. I'm adding 1 to them all. So I'm going to end up with this. Right? And that's how to think about it, because that's how you'll get this conclusion. Okay? We really did most of the work at this stage, thinking about all the possible output values from x squared. Once you figure out that that's all the non-negative numbers, then you know that if you just add 1 to them all, you're just going to shift the unit, or pardon me, you're going to shift the range over 1 unit to the right.